Continue this morning's program with Armas from the University of Amsterdam. Will tell us about fluctuating hydrodynamics of open-driven systems.
Yeah, thanks a lot for inviting me here. I'm going to present some work I've done with a few people at the University of Amsterdam, if this gets to work. Yeah. So these two over here, Akash and Ruben, and Tuan and Wout if I get there. So let me start with my motivations. I think this will be maybe slightly different than some of the talks you've heard here, but I'll try to convince you that it's interesting. So I've made this as broad as possible. So what are my motivations? My motivations are, trying to understand all forms of matter in the universe. Some of here you probably recognize. So there's superconductors and ferromagnets and quark-gluon plasma, and there's some illustrations of spin ice and strange metals and charge density waves and all sorts of things that you can see there. These ones might be difficult to recognize. This is my illustration of a black hole in higher dimensions, and this is a deep brain in string theory. And then that point over there is gravity itself. That some people also think of it as an emergent phase of matter. Okay, and so I want to understand all these things because I'm a megalomaniac. And what are the principles that govern matter across scales? So that's sort of my question. Okay, and one of those principles we know for sure, it's about symmetry and symmetry breaking patterns, right? And in the past, few years, people have sort of enlarged their notions of symmetries in physics. It was there in mathematics for decades, but they started creeping in physics in the past decade. And so you see some symmetry breaking patterns here on the left: spontaneously broken, unbroken, explicitly broken. You've seen this before. Now these days we talk about approximate, so that's like weakly explicitly broken, pseudo-spontaneous, both spontaneous and explicit, and then you have anomalous, and then this one here, temporal spontaneous symmetry breaking. You wouldn't ever heard about it unless you would be my biggest fan because I came up with it. So, and then there's several types of symmetry that you can see on the right-hand side. There's time translation, spatial translation, rotations, U1, and then the generalized global symmetries, higher form, higher group, and then also other kinds of symmetries which are more space-time symmetries, dipole symmetries, and boost symmetries, okay? So I'm going to focus on some of them. And of course, as you know, these symmetry breaking patterns, they actually work for different systems across scales. As you can see here, these are all systems that have, for instance, spatial translation explicitly broken or spontaneously broken. And they're very different types of systems. Let me just give you some examples of these things. One of them I put here, the one below, because I had a dinner conversation yesterday that made me do this. But the one that I'm more interested for this talk is the top one. So this is an exact U1 symmetry. You have a conserved current, a U1 current. You can integrate, you have some point particles in there that are charged particles or the density of particles. And then you integrate this thing over a box and you have a conserved charge. On the right-hand side, that's an approximate symmetry. So that's capital. The small L is just a bookkeeping parameter. It says it's small. You should take that thing as small. And then there's an L, some kind of operator that breaks the symmetry. And now what happens is that your particles can just become two particles, or two particles can merge into one. Since that L can have some arbitrary value, according to me, then you can create particles or remove particles from your system. So that's what means that if there's an approximate symmetry. This is a higher form symmetry, a U11 form. So now, instead of counting points, you actually count the number of lines that cross a plane. And those intersections, you can integrate that, and that's a constant. That's a charge. That's a U1 charge, because if you move the plane in this direction, these lines never end. So you have a constant number of lines. Okay, so this is the symmetry of electromagnetism. And now you can have an approximate U1 one-form symmetry. And what that means is that there's points where the lines can meet or the lines can bifurcate, okay? And then, you don't have a conserved charge anymore because of that. But because this is an antisymmetric 2 tensor, you can act with another derivative, and So I'm just repeating the same thing here. And if you act with another derivative over there, this is automatically 0. So you get a topological symmetry. And that's precisely now counting the topological defects where these lines meet or bifurcate. Okay. So every higher form symmetry comes with an associated, every explicitly broken higher form symmetry comes with an associated topological symmetry. All right. So what we do with this, we can classify phases of matter. This is just rotation and translation invariant, a gas or a liquid. This is spontaneously broken spatial translations, crystal. We have spontaneously broken U1 symmetry. A plasma is a temporal spontaneous symmetry breaking U1 one-form symmetry. A spin ice is a pseudo-spontaneous U1 one-form. Superconductor is a pseudo-spontaneous U1 one-form plus spontaneous symmetry breaking of emergent U1. And a D-brane is a spontaneous symmetry breaking of a higher group that I didn't talk about, okay? So we can do this with this kind of stuff, but is this all that we like to explain? Are these all the types of matter that exist in the universe? They're not. Now I added a lot of phases here. I added a so-called active crystal made out of starfish embryos. I added a map of the Netherlands. I added the metamaterial made out of these units. I added some things called active liquid crystals that are made out of bacteria swimming around. Okay, so these are other phases. And the question is, does these symmetry breaking patterns that I just showed are sufficient to describe those phases? Oh, there's gravity there as well. So I can organize these things in what's called passive matter, which is everything that I showed you before. And I can put the other thing over there that I claim now is active matter. All right. So those are the phases I want to now try to describe. Oh, sorry, gravity.
So how is the map of the Netherlands active matter?
Yeah, let's come to that afterwards. So passive matter, here I have a crystal, here I have what's called an active crystal. They both have spontaneously broken spatial translations. So this is not sufficient to just say, spontaneously broken translations doesn't distinguish the two phases. Same thing here, I have a real passive liquid crystal. Here I have another active liquid crystal, and they both have spontaneously broken rotations. So it's not sufficient. People have come up with some classification in active matter literature that describes things as dry or wet, but this just means whether there's a flow or whether there's no flow. Either the material relaxes the flow so quickly that you just forget about it, or it's wet and actually can flow. But this is also not sufficient. This just tells you that there's some systems in which there's spontaneously broken translation, or explicit broken translations or not. So what is, first of all, the difference between these systems? And because people like to use active matter as a proxy for living systems, what is the difference between living and not living kind of things? So I did some ChatGPT searches, and I know that Blaise hates this because I created a lot of CO2 with these searches. But then, ChatGPT just says, these systems, active matter, they can generate motion spontaneously. They have swarming behavior. They challenge equilibrium thermodynamics, fluctuation dissipations, and things like this.
Is ChatGPT active matter?
I haven't looked at neural networks, but but maybe who knows?
I think ChatGPT do better than Wikipedia for this definition.
It does, yeah, it does. At least it summarizes things in a way that
No, but there's two paragraphs. You don't find the same.
No, not the same, but okay, but I don't. Let's forget about the ChatGPT story. So if you have to summarize, there's these kind of characteristics: energy input, non-equilibrium dynamics, novel collective behavior, breaking of FDT, some kind of notion of effective temperature. All right. So basically, when you have a passive matter, there's always a notion of entropy you can come up with. There's a second law of thermodynamics that has to be held. That's what that equation is. And then all these things come with it. Equilibrium thermodynamics, FDT, detailed balance, all kinds of stuff. So what comes here? All right, what is that? And what I will argue is that the thing that distinguishes all of this is that these phases have an approximate time translation symmetry. Okay, so time translation symmetry, which is associated with energy conservation, is weakly explicitly broken by something. All right, and I will tell you what that something is. So this is my perspective. I'm going to work at very coarse grain level. I'm not looking at microscopic models and see what happens. I'm just looking at the continuum description, and in that continuum description, where we have a very controlled hydrodynamic approximation to things, I think of it as having a system, in contact with some environment, and I drive the system in some way. For these sort of living systems, the drive is internal because each of the microscopic constituents burn some energy of some kind, if they're made out of bacteria or whatever they're made of. But in general, you can just think, I'm going to drive the system somehow. Okay. So this is my outline. I don't know how far I will reach, but I'll reach as far as I can. And I stop there. So hydrodynamics, for those who do not know what this is. You have some microscopic system. It doesn't matter what kind of microscopic system it is. It can be an agent-based model, spin glass kinetic theory, could be holography, can be experimental design. You build it in your lab, whatever. And I just zoom out of this system. I coarse grain stuff. I treat the system now as a continuum block of stuff, of matter. And I identify what are the relevant collective variables and the symmetries. And I end up with some collective variables, such as temperature, chemical potential, flow velocity, Goldstone fields, that then describe the collective behavior of that block of matter, whatever the microscopic says. That's hydrodynamics. In more field theory language, what that means is that you have operators in your theory, and you sort of expand your operators. You write constitutive relations for these operators in terms of those variables, and you expand them in a derivative expansion. Okay, you count for more gradients and more gradients as an attempt of figuring out more what is the fine structure of that block of matter. So hydrodynamics, from this point of view, is just low energy, non-equilibrium effective field theory, is a universal language for this collective phenomena that seems to only care about symmetries, degrees of freedom, and the laws of thermodynamics. Okay, and you find it everywhere, and I'll just show you. Where do you find it? You find it in gravity. If you take a black hole and you perturb it, in some regime, it behaves exactly like a fluid. You find it in traffic flows. If you have a bunch of cars moving on the street, you put a camera from the top, you record that video, you fast forward the video, you get a traffic flow. You find it in crowds. So these people doing a marathon in Chicago, and on the right-hand side is the density waves as they move. This is also described by hydrodynamic effective theory. And if you believe all that, then you take everything else. Plasmas are also described by hydro, quark-gluon plasma, electron flows in graphene. Okay, it's all over the place. It describes the collective phenomena of all these phases of matter, near equilibrium. So let me say how we do this in practice. This is the hydrodynamic construction of water, and I'm calling it passive water. So you can just take it as the water in that bottle over there. And these are the symmetries of that water over there. There's energy conservation tied to time translation symmetry. So there's a conserved energy density. There's momentum conservation tied to spatial transition symmetry. So there is a conserved momentum density. There's a continuity equation for mass density. That's what it says here. There is a Galilean boost symmetry. So in this world, non-relativistic. So there is this symmetry in most systems. Of course, you can also break that, but that water has Galilean symmetry. And then the collective variables are the temperature, the mass density, and the flow velocity. And you have a second law of thermodynamics that tells you that this entropy density has to be positive semi-definite. Okay, this is the construction of the symmetries of water. And what do? We take those variables and you write the most general constitutive relations for those currents that you see here. Okay, I have to expand these currents in terms of the collective variables and its gradients. I do this iteratively at a given order. And what you get, for instance, for your stress, is that you get shear viscosity, a bulk viscosity, and here for your current, energy current, you get thermal diffusion. Okay. And the second law restricts these things. It says all these coefficients have to be positive semi-definite. Okay, you measure this for water, they behave like that. All right. Relativistic water. For those who like relativistic water, it's the same kind of story. Conservation of stress, U1 current, second law. You do the same thing, and you find conductivities have to be positive semi-definite, etc., etc. Okay, same thing. What about this active matter story? There's 2 reviews of active matter, how to do hydrodynamics of that. And it, in a very rough caricature of it, it goes like this. You take your equations for water, and now you want to make this water active. You throw some bacteria into that bottle, and you see what happens, okay? And what you see from these reviews is that this is what happens. You forget about the energy conservation. You forget about temperature as a collective variable, because if you throw out the energy, you have to throw out some variable. And you forget about the second law of thermodynamics. Then you do exactly the same kind of approach as I did before. And now you have these currents here, and you expand those currents in gradients. And what happens? Well, you get the same answer at this order and with these symmetries, but there's no second law to constrain this. So in an active system, a priori, these things can be totally unconstrained. They can be even negative, okay? So this is the procedure. If you want to turn anything active according to those reviews, or according to how people have been doing active matter in the past, is that you write the equations for a passive theory, you kill the energy, you kill the temperature, you kill the entropy, and you go ahead with it, okay?
This is really what they're saying?
Yeah, I mean, let's say it's a practical way of doing what they're saying. There's some more evolved way of doing something, but still doesn't constrain the system. But there is a more way of trying to introduce fuel, still forgetting about the energy, that allows you to systematically derive the terms in the equation for those currents, but still forgetting about the energy and the temperature in the second law. But there is a way. It's one of those reviews is sort of more detailed than the other. But I can explain it later if you're interested in knowing that. So let me do it differently, okay? I'm showing this because the way I'm thinking about it is similar to the way that has been recently developed for breaking of spatial translations, okay? So if you have a lattice, these are points in the lattice, the Goldstone fields that describe the lattice, they basically tell you the position of the lattice points, okay? This is just a material science perspective on crystal geometry. So, once you have lattice fields, you can, they have some shift symmetry. You sort of define the gradients of those things that are invariant of those shift symmetries. And then you have an induced metric on the lattice, which is just the gradients of those things contracted with a material space metric that stays constant in this case because there's no plastic deformations for that. So once you have this, you can also, that's the description of a spontaneously broken lattice, a spontaneously broken translation, so a dynamical lattice. But you can also think of a system, or many cases in which you forget about the dynamics of the lattice, you freeze the dynamics of the lattice because you say, for the specific phenomenon I'm interested in, the oscillations don't matter so much. So now you have something interacting with the background lattice, if you want to describe that, like a ionic lattice that is in the background. Then I'm just changing the variable from a dynamical Goldstone field to a background field that describes your lattice. Okay, and what happens when you do this is that your symmetries now change because the background lattice breaks spatial translation, as you see there, but nothing else. Okay, so your momentum equation now becomes relaxed because of that thing. And if you go ahead with this, what you find is that if you turn the crank on the hydrodynamic procedure, if you take a background lattice that is just homogeneous, then you end up with this term on the right-hand side of your equations, which is momentum relaxation. Okay. If you're from
Does it matter that in crystals the momentum relaxation is only umklapp versus like?
So here I'm being agnostic about what is, I'm working with no microscopic system. I'm just working at symmetry level. So
No, but at symmetry level, there's a difference whether you break translational symmetry down to a subgroup or whether you completely break it.
Yeah. So here it. I don't think it will change this part. Maybe it changes more. There's maybe more structure afterwards if I do a complete analysis, but it doesn't change this relaxation bit.
It changes it in the fact that now, if you were to do umklapp, then this gamma would be fixed in terms of some other parameters in the theory.
No, sure, but that's just the form of gamma.
In your construction, this is going to be completely unconstrained.
Yeah.
If you were to do umklapp hydrodynamics, then this would be set by the viscosity.
No, sure. So
yeah,
but then it changes, but then it's microscopic. It changes the actual parameter, but not the structure of the equation. That's the sort of the nice thing about Hydro.
No, but in one case you have a residual symmetry, no? That's why it's not a microscopic thing, it's a fundamental symmetry thing. There's a fundamental symmetry difference between a crystal and an amorphous solid.
Yeah, so that kind of thing that you're just saying, it won't show up in this coefficient, but it will show up in other coefficients in the theory, in which that discrete structure that is left still has an impact. Yeah, but not
show up here. Because here you're assuming that momentum is relaxing isotropically.
Yeah, all right.
If you spontaneously broke translations down to a non-isotropic crystal,
all right,
then this would now have to respect the
leftover. Here there's rotational invariance. That's true.
Yeah. Rotation is also reduced to some.
Yeah. So that could okay. I take it back. It could change this to a more anisotropic thing. That's true. Yeah. Okay. So the second law then constrains this guy to be positive semi-definite, okay? And so you have momentum relaxation. And if you look at the collective excitations, you see that the gamma exactly enters here, this propagating mode, exactly in the way that momentum relaxation physics should, okay?
Up to an overall minus sign.
Yeah, that's sad. But okay. Sorry. That's sad. Yeah, but anyway, I agree. So active matter. So my point in the beginning was that only time translation is involved in this story. So forget about all the other equations that I showed you in the system, because you get the point with just these two equations. There's an energy equation and an entropy equation, okay? And this is what I'm going to modify. So first, I'm going to consider the fact that the system is driven by something. I introduce a field, like I introduced a background lattice, but now I introduce some kind of driving field. So a field that injects energy into the system. And that's a coefficient that I put in there, which is the rate of fuel entering into the system, okay? And the L is again a bookkeeping parameter because I want it to be small, all right? So if I drive the system, I just add a term that injects energy into the system, all right? And this I call a driven system. But this is not sufficient, because if you just have a system, imagine that your fuel is constantly injecting energy into the system, your entropy, your temperature is just gonna go up to infinity. And that's not something you want, right? Because everything would go into internal combustion if that would happen. So this cannot be the full answer. So now I'm gonna add another field, which is an environment field, okay? So, oh, sorry, it's blue, it's a bit too bad. But it has exactly the same structure. It's just called phi E and RE, all right? And RE is now the rate of exchange of energy with the environment because it's open, all right?
Sorry, what is epsilon I? Momentum density.
Sorry?
Epsilon I?
Oh, energy. Energy current.
Ah,
okay. Yeah, right? So this is the same, the first equation I showed you in all the slides before. But if it's open and it is allowed to exchange energy with the environment, it's also allowed to exchange entropy with the environment, okay? And what happens is that your second law gets modified there. I'm sorry for this. This is L, this is Boltzmann constant, this is the rate of exchange with the environment, which is this rate that is here. And that has to be positive semi-definite, okay? And now I call this a driven plus open system, and I say, that's active. That's my definition of active. So let me look at entropy production. So what this kind of story tells you, as you can see here, is that the system entropy can increase or decrease as long as the entropy that is dumped into the environment can compensate for it. So the entropy of the universe is still positive semi-definite, even though the system entropy can decrease. Okay? So that's kind of a hallmark of non-equilibrium systems. So let me choose a very simple system in which the environmental temperature or environmental field is always at a constant temperature that I call temperature of the environment. The drive force is always constant. I call that delta E. So it's always dumping energy into the system at a constant, always the same for all times. I'm now focusing on no flow, so forget about momentum. And then I'm just reminding you of the first law over there. And if I put this whole thing into here, and I look at what are the constraints imposed by this equation, by the second law of the universe, what I find is that both the rate of fuel and the rate of exchange with the environment have to have this form, in which delta T is T minus the temperature of the environment. So it's the difference between the temperature of the system and the temperature of the environment. And these coefficients of fuel exchange have to be positive semi-definite. Okay? So there is some constraint on the rate of exchange with the environment and the rate of fuel injection. Okay. If I put that whole thing back into the entropy equation, I get that entropy. I should say something here because sorry, but now this is the price to pay for animations. I have to go back and forth, back and forth. Is that I focused on a totally time-independent state. Okay. So I'm just looking at time-independent things. And for time-independent things, I still get that the entropy of that state that is time-independent is not zero, but producing entropy all the time. Okay. In passive hydrodynamics, that will be impossible because any time-independent state will not produce entropy. That's the notion of hydrostatic equilibrium. Here, temperature-independent states are always producing entropy because there is a fuel injection and the gradient in the temperature. Okay?
But it's not really time independent because you turn on time dependence. So
well, there's a time independent. Yeah, there's yes, but your energy density, all this kind of stuff. Yeah.
Yeah. There is some fields.
Well, there's it's true that in that sense the source has time there. That's true, but.
Because otherwise, I could make the same argument for the momentum relaxing case that you described earlier, where nothing depending on space other than the capital phi I fields that were linear in X.
Yes.
And then all X dependence dropped out from everywhere else.
Yes.
And momentum relaxed and entropy was produced.
No, entropy is not produced in that case.
Capital phi I plates.
No, of course not.
This is gamma.
No, it's not. For a time-independent state, no, that's passive hydrodynamics. It's in agreement with hydrostatic equilibrium, no matter what gamma is. Of course not. It cannot happen. No. So I can also look at what T has to be in this time-independent state, the temperature of the system, with respect to the other variables. I literally ask for this to be time-independent. I don't have any flow, so there's nothing that can be here. So this left-hand side is zero, okay? And if the left-hand side is zero, this right-hand side has to be zero, and that tells me what T0 has to be. It's as simple as that, okay? Because if you remember, the rates depend on delta E and delta T. So I can solve delta T to find this relation, all right? And the interesting thing of this is that it says that the system temperature has to always be greater than environmental temperature because this factor here is positive always. When you think about living systems, that's kind of what happens. Is that simplified things, but the temperature of your system is always higher than the temperature of the environment. It tries to be. Of course, we have more other kinds of mechanisms to deal with the fact that sometimes the temperature of the environment can be higher than your body temperature, but that's it. I'm not including those mechanisms here. But the basic one is this one. I just say, recall ChatGPT because you did mention the notion of effective temperature in this system, and that's kind of the thing there. Okay. All right. If you turn off the fuel, the drive, this whole factor goes to zero. And then you equalize with the temperature of the environment. Okay, makes sense. And if you open the book of Schrödinger, What is Life? It says, when that happens, when you thermalize with the environment, you're dead. That's what passive matter does, right? It thermalizes, but active matter does not. And if you look at propagating modes, then what happens is that your energy mode now becomes relaxed with that relaxation, gamma E that I defined over there. Okay. So you get the same kind of momentum relaxation, but not momentum relaxation, you get energy relaxation.
I think the fact that you have a purely dissipative mode is a hallmark of entropy not being conserved, going back to momentum relaxation. We're exactly the same.
Entropy is conserved in that case. I'm sorry. I mean, you must have done that yourself. I mean, if you want to, if you want to look at equilibrium in momentum relaxed hydrodynamics, as we've worked on it, as you worked on it, the equilibrium state does not produce entropy.
I agree with this.
If you have a dissipative out of equilibrium state, of course
in momentum relaxed hydrodynamics. The analog mode, the one that you showed before, this is an out of equilibrium mode.
I mean, the gamma comes as a dissipative term. I agree, but here this guy is not.
Fine.
Yeah. Okay. So there's a difference there, because this guy comes from the coefficients that are showing there already at ideal order. Mm-hmm. Okay. So there's a difference there, but okay, I get your point now, but. Okay, so this is my point of view now. If I want to make active water, I take water, the water system, passive water, but now I break time translation symmetry by introducing fuel sources and environmental sources, and I have an approximate second law of thermodynamics. Okay, and the rest just goes through. If I apply now this to water, what happens? I'm highlighting the coefficients that are new. These are the coefficients that show up if you include the fact that there is this approximate time translation symmetry. And in this active literature, these coefficients here that appear in the stress, I will never be able to compare this with any active literature because they don't consider the energy current to begin with. But in the stress, I can compare with them. And this is what's called swim pressure. It's a contribution of your active dynamics to the pressure itself. That is not thermodynamic. All right. And another interesting thing is that the eta coefficient then gets a correction, small correction. You see, it's not just the viscous correction that you normally have, but a contribution comes to it. Of course, I'm doing this perturbatively, so L is small. If L would be big, I wouldn't even have the energy conservation to begin with. So L has to be small. And of course, this will never, within this regime of validity, will never be able to drag the viscosity to negative. But there is something coming in that changes the viscosity from what you usually consider. So there's an active contribution to the viscosity coefficient. All right.
This is because here you've picked out this specific form for the source linearity.
Yeah, sure.
Otherwise, this would show up as a different term.
I honestly, I don't have a lot of to say about other types of sources, but I guess this would end up with something like what you mentioned of umklapp in the case of, I mean, if you do spatially varying sources like in momentum relaxation, then there's more things that can happen. I don't know what would be, but I would have to literally put a source, see what happens. I don't know. But this recovers, what I want to make clear is that this recovers everything that has been done in the active matter literature. Okay. That's what I want to be clear about. But I'm now putting the principle on it. I'm saying, there is actually an approximate symmetry that distinguishes these systems from the whole other thing that we had before. Yeah.
So maybe this is a bit of a weird question because I'm not very familiar with phrasing symmetries in these type of equations. But if you look at the active hydro equations that you wrote, they look time translation symmetric to me. You just have a constant fuel input and a constant dumping into environment thing. But the way that I intuitively explain time translation is laws of physics are the same now as they are in the future.
Yeah.
So
yeah.
If I look at like a Hamiltonian system, which I usually look at, I either have a Hamiltonian that's time independent and I have time translation. If a Hamiltonian is time dependent, I don't have time translation. But it looks like you have some time translation, right?
Yes, and this is the trick. When you add these background fields that break the symmetry, you literally off-shell when you write the whole Lagrangian for your theory. Off-shell, it restores the symmetry. But when you pick the source to be something, like I'm doing there, the source to be time dependent, then it breaks it. This is a trick to sort of have the whole thing under control, to understand.
But a constant influx of energy is not time dependent.
It is. You saw the source I picked. So the source
that might help.
So you mean because the source was delta E times T?
Exactly.
Okay. Think of a magnetic field. It appears on the right-hand side of the momentum conservation equation. At the level of the theory, it doesn't break. The theory is still translation invariant. The state that you pick for your external gauge field that sources the magnetic field is not, because AY is B times X. Yeah, and so effectively it relaxes momentum and it drives your motion into cyclotron motion and associated damping mechanisms.
Yeah, but in the case, so maybe that's why if you use that analogy, my question then would be if in this case of the magnetic field applied to a 2D system where you would look at the cyclotron numbers and stuff like this, you still have magnetic translation. There is a concept of translation. It's just no longer a commuting group. It's a more fancy symmetry, but you have magnetic translations. You still have translational symmetry if you put a 2D field in a magnetic field. Choosing a specific gauge breaks it, but there is an abstract magnetic.
Exact Galilean symmetry.
So it's not Galilean. I'm just saying that there's a translation operator.
You're saying that you can shift P to P minus EA.
Yeah.
That only holds because of Galilean symmetry.
I mean, more. Yeah. Normal. Yeah. You can look at the symmetries at the level of the generating functional. Okay. And at that level, the fields I put in don't break the symmetries. But if I fix the field to be something, it breaks it. This is sort of the idea. And of course you can see immediately there that if you have time translation symmetry, you should have energy conservation that you don't have. I mean, it's just.
Yeah, no, but you said just delta E times T, that already consists for me.
Yeah, okay.
Or even what you were doing with the spatially dependent chemical potential. Your theory was perfectly translation invariant to begin with, but then you picked the state, you engineered the state where the chemical potential had some spatial dependence.
Yeah, but then the Hamiltonian explicitly does not have.
Hamiltonian was symmetric.
No, it was not.
The off-shell.
Yeah.
But
I would say in my case, the Hamiltonian has broken translation symmetry.
Maybe because you fixed the sources.
Yes.
You fix the source, then yeah.
Okay.
Yeah. So I'm gonna go. I don't. Yeah. I want to give you a Lagrangian for this. Okay. But there's a lot of stuff that for me is hard to introduce in short notice. Short amount of time. So I'm going to just say what the ingredients are. Okay, so this is how do I do a Schwinger-Keldysh construction of these theories. Okay, so I'm after a generating functional of this kind, in which these are the collective variables, these are the noise partners of the collective variables. This is an action. These are the real sources. These are the stochastic partner of the sources. So these are all the ingredients that you need for a Schwinger-Keldysh effective action. Okay. Now let me give you a bit of a flavor where they come from. This is what I want to compute. I want to compute expectation values. I want to compute retarded correlation functions. I want to compute symmetric correlation functions. And I want to do this because I want to test whether equilibrium thermodynamics works for these systems or not. Okay, so I need to compute symmetric correlation functions to do that and test FTT. So this is the statement of FTT. Retarded correlation functions on the right-hand side, symmetric correlation functions on the left-hand side. And then also Onsager's statement over there, also of equilibrium thermodynamics. Okay, I want to check whether this holds for the systems I looked at. Okay, so I need to introduce geometry and sources into the system. Okay, so if you have a continuous U1 symmetry, you can do this with the Kadanoff-Martin method, in which you can compute retarded correlation functions by adding sources in the appropriate way. There's issues with this, especially once you want to look at systems with approximate symmetries, and if you want to compute correlation functions for currents rather than just densities. So a better way to do it is by using background source variation, and that's why I need to introduce sources. Now I'm looking at systems that are non-relativistic, so I need to use what's called Newton-Cartan geometry or Aristotelian geometry. So I need to introduce these vectors here. So this is a kind of degenerate metric story. There's a kind of a metric for time and metric for, we cannot even call them metrics. There's a ruler and the clock form, and there's a gauge field for the mass. And I can compute correlation functions by looking at these variations with respect to these background sources. So this would be for the energy density and energy current. That's the clock, that's the ruler, that's the gauge field for the mass. Okay. If you've never seen Newton-Cartan geometry before, this is how it looks. This clock form gives you a kind of foliation, and at each value of the clock form, you have a special structure. If you have Galilean boosts, that's called Newton-Cartan. No boost, that's called Aristotelian. Then you need noise fields, okay, to compute symmetric correlation functions. And now you're entered the realm of fluctuating hydrodynamics. There's a prescription for how to do that. You introduce some kind of random variables over here that are Gaussian, have this mean over there, and this allows you to then compute exactly the symmetric correlation functions that look like this. Okay. Typically, you do this very phenomenologically. You literally introduce the random fields, you compute the symmetric correlation function, and then you impose FTT by hand by comparing with the retarded correlation function that I did with Martin Kadanoff or background variation method. And I fix that delta, which is the mean of the noise, to be of this form. Once I do that, that's equilibrium thermodynamics. All right. Where does the noise fields come from? Is because once I have that random variable, I have a path. I have to define a path integral over all noise configurations. But then you can turn this into a multiplier times the equations of motion, and then you integrate over all noise, and you end up with, for instance, the stochastic partner of your density. Okay, so this is the Martin-Sigia-Rose construction, or MSR. All right, and the Schwinger-Keldysh construction is just a kind of MSR on steroids. That's the thing I kind of explained in the beginning. And you can do that from a symmetry point of view that I'm not going to go into it. But here I just want to show that if you do this very formally and you construct this action, you can compute, for instance, the retarded correlation for density-density and the symmetric correlations for density-density. This is actually in what we call an active superfluid. So you literally take the superfluid, passive, but you make it active by doing this approximate symmetry story. And you can see that the fluctuation dissipation theorem is violated. Okay. So as soon as you have these active constructions, the way I presented, in which you break time translation, when you lift this to a Lagrangian, a non-equilibrium Lagrangian, you can compute all the correlation functions, and they violate FTT. Okay. So these systems are really showing all the non-equilibrium physics that you expect them to show, and that people have discussed, observed in the literature. Okay. So this is the construction, Schwinger-Keldysh construction. I put in the symmetries of the phase of matter, including the approximate symmetry, plus some other symmetries that make this path integral well defined. And then I have to define what's called the KMS symmetry acting in all these fields. And you kind of have to generalize your KMS symmetry for environmental fields. That's what we call active transformations. It comes with an extra I in one of these transformations that precisely makes sure that everything is fine when you actually go to an equilibrium state and becomes active when you're outside this equilibrium state. Okay. This is a lot of sorcery, I understand, but I don't have a lot of time to go there. So how do I get this from an action? How do I get these equations from an action? This is how it looks. It's awful, but that's how it is. It has these N fields that describe the coupling to sources of the geometry. It has the B fields, which are associated with the gauge field. And then it has the fuel counterpart. So fields, Schwinger-Keldysh fields for the fuel and the environmental field. Both the normal, the real source, and the stochastic partner. You put it into a Lagrangian, you now vary the Lagrangian, and you get precisely these equations, okay? With contributions coming from random variables as you continue this. So you will get the stochastic terms that I was talking about, okay? You can do this now for any system. The most common system in active systems is so-called active nematic. So there's spontaneously broken rotations. There's an active nematic tensor that you can write in terms of a director field, this PI, that tells you the orientation of your whatever weirdly shaped molecules. And you can do the exact same thing. Now you have also nematic fields, the stochastic partner of the nematic fields. But you write that, you have to decide what kind of crystal you have, whether it's homogeneous or not homogeneous. So this is Franck's free energy plus some other stuff, plus that thing for a homogeneous. Forgot now what is the symmetry of this guy, but yeah. So depending on the symmetry of the liquid crystal, you have different free energies. And this is what you get. For instance, if you vary that action, you get these 5 minutes. You get these not according to this guy. Okay.
So you have 5 minutes for questions.
Okay. All right. So yeah, you get these terms in blue here. These are the energy current. Forget about that. This is because that is not in the active matter literature, but this one is. So this is this kind of swim pressure again, and this is the most important term in active matter literature because it's what is responsible for what's called active turbulence. So when you run these systems of these active nematics, it can develop instabilities, and there's these beautiful patterns these things make that look like swirls, but they're not turbulence of velocity fields, they're turbulence of the nematic director, okay? And that's because of that term over there that you can derive precisely by just varying this Lagrangian, okay? And you derive the corresponding effects in the energy currents, all right? You can actually apply this to try to see if you can convince some experimentalists to now look at energy-energy correlations, okay? There is a nice Dutch story in which they looked at the out of equilibrium fluid by just putting the fluid between two temperatures. This is by Sengers, who is actually in the US. But I think some of these experiments were done in Leiden. And when you look at energy correlations in an out of equilibrium system like this, it actually can have features like this one. It goes with 1 over k squared because of the non-equilibrium nature of the system, which is the delta T. So actually the energy correlations can give you signatures of, the fact the system being out of equilibrium. And that's why it's important to include the energy in your framework. Another famous experiment is what's called a confined nematic. So you put this 2D nematic between two plates, and you can change the distance of these two plates. And if you increase the distance after a certain value that is set by a critical wavelength, it goes into what's called a spontaneously flow transition. Actually, it just starts flowing as once you cross that critical value. It has been shown experimentally, so it's not a joke. And what you can do now is you can look at exactly the same system, but look at what temperature profile will the system have if I include the energy dynamics into it, okay? And it actually has a profile of this form, depending on what kind of boundary conditions you impose. So if you could measure the temperature of these systems, which I understand is challenging, if you could measure, you would find a signature there of how the temperature is varying across the slab where you can find the nematic. Okay. So it could have some interesting consequences. So I have what, 1 minute? 2 minutes, basically. Now, something that I would like to do is to start simulating these things, okay? And I'm more of a theorist writing equations. I would like to simulate these things. I want to simulate fluctuating hydrodynamics, all right? I want to simulate the fact that these things are there, but they also have fluctuations, so I can measure correlations. I can do all kinds of stuff. And this is something I've been working on. And this is and instead of going full on with flows and stuff, I'm just trying to set up the system with just diffusion, for instance. And this is a very simple system which is sort of the microscopic system of a Kahn-Hilliard model. So these are two types of particles that hop in a lattice, where there's like empty sites in white, and there's a free energy landscape that is described by this, that, they look at whether their free energy is minimized if they move over there, and if it's not, then the probability of hopping, decreases. If it is, it increases. And it makes, sort of these phase separation kind of things. This is a microscopic simulation, okay? You can make it slightly more complicated and also add exchange. So particles can exchange from different types, from blue to red and red to blue with a certain probability. You get these other also phase separating patterns. Actually, in the long run, they all turn up to be just one color if you wait sufficiently and long enough. Now, there's a way of taking the continuum limit of these lattice models. This is known as the Doi-Paliti path integral procedure. And there's a whole thing over here that I'm just going to show you. You have to do some transformations. Then you have to take the continuum limit, the lattice size to 0, you scale stuff, and you end up with hydrodynamic equations with noise. So these are just diffusion equations with noise, but complicated, okay? And you end up with a free energy that has exactly the same form as the Kahn-Hilliard free energy, but now these coefficients can be also antisymmetric, okay? That's why it's active, because it kind of broke the symmetries that a passive system does by introducing non-reciprocal interactions, all right? There's some coefficients there that come with the lattice size, and as you can see in 2 dimensions, this one just becomes 1. So the noise becomes super important for certain types of exchange models, okay? These are the fluctuating hydrodynamic equations. I can massage them into this form. This is the picture. You start with some lattice model and you coarse grain it, you get a hydrodynamic model that is driven by free energy, but also by this exchange current. And then you can do simulations for different kinds, depending on what you put for these coefficients. So this is a case in which particle blue doesn't like particle red, but likes other particle blues. Same thing for red. And then what happens is that you have this phase separation. In this case, for instance, particle blue doesn't like particle red, but particle red likes particle blue. And then you get these lava lamp kind of patterns in which, the blues are trying to get away from the reds and the reds want to try to become blues. Okay. So you can have all sorts of phases. This is what happens if I also put the exchange. The pattern becomes a lot more noisy because the noise is very important for that exchange model, while for this one, the noise is subleading. Okay, and the fluctuations are much less. You can sort of classify the phases that come into this system depending on the ratio of how the different mechanisms, the strength of the different mechanisms of exchange or hopping. And there's very nice phases that you can come with different names. There's phase transitions. So here, for instance, there's something that stops over there. This phase here, the segregating regime, stops after you increase the diffusion of particle exchange. And then if you introduce noise, these things become a continuous, which is sometimes, it's not unknown that when you introduce noise, the phase transitions can kind of disappear and then you just have crossover. Okay. So you can classify all these things. This is sort of an example of a trajectory of over time. You can look at stability. And of course, what happens is that if your system is unstable, then it's going to develop this pattern formation. If it's not, it doesn't develop this kind of stuff. Okay, very quickly. So I showed you a lot of stuff. These active systems, whatever I call it, active systems, they don't need to have non-relativistic symmetry. Once you understand that the symmetry breaking pattern is time transition symmetry, they can actually be relativistic. So you can also model relativistic systems in this way if you have a reason for it. Here I have like bacteria traveling at the speed of light, which is of course not something you want to maybe model. But you can think of modeling even plasmas in this way because you might have both injection and extraction of matter to keep the accretion disk stable, for instance. You can think of it in holography. How would you make this guy in holography? I really wish I knew the answer. People know how to do momentum relaxation, but I have no idea how you're going to get this approximate law of entropy out of this. It would be amazing, whoever managed to make that. And then there's loads of questions like, can you actually measure these energy correlation functions for these kind of systems? How do you uniquely define temperature? There's a whole literature, what happens of entropy in this kind of driven systems. Another interesting thing is coming up with a microscopic model of heat exchange. There exist several, but now you will have to go there and modify it to make it open. So this is something we're looking at. How do you make a microscopic model of heat exchange, an open driven system? You can, solve these things. You can now generalize this code that we kind of developed, fluctuating hydro, to the full model, including the heat and the flow, etc., and see what happens. The codes are not so simple, just so you know, and it takes really a lot of CO2 to run them. There's more general theories you can consider because I actually didn't back-react the fuel source. There's more transport coefficients if you want to do the most general theory possible. Okay. There's new phase transitions that you can look at. You can also think about kinetic theory for these systems. And then, believe it or not, there's people discussing, these kind of systems also in quantum systems. It's slowly coming. So I think it's in the past few years, you see all sorts of active quantum matter. You see open quantum systems and non-reciprocal interactions. There's even a recent paper on engineering active motion in quantum matter, active quantum flux. So, the question is, also for me, how relevant it is for the quantum realm, these things. But it seems that in some way it's possible to design them in such that it mimics some of these features. And it seems that this is coming. Okay. Thank you.
Any questions?
So these systems, if you look at the fluctuations, they're always stable.
You're what?
You always have stable modes.
So when you do these non-reciprocal things,
No, at the very beginning, when you do this hydro with
in these ones, yes, that's true. The very beginning, yes. Not in these systems I showed you, because then I was breaking the entropy laws, so to speak, by allowing the coefficients to be whatever they can be.
so okay, if you break that,
then you'll end up with instabilities, and there are those instabilities that gave rise to this kind of pattern formation kind of story. Yeah, but if I don't break that, then the system will be in principle stable. Yes. Yeah. When you add pneumatics, there can be instabilities that you have to fix, typically by also adding momentum relaxation. Yeah, there can be. But that's just because it's a different kind of equation. It's a Goldstone kind of field. It's not, so there's a different story there.
Because you do have still the second law, just to kind of modify the second.
Exactly.
So, but often if I just write down a microscopic theory of something, there is no second law at all. So somehow that has emerged when you look at a hydrodynamic description. Is there a way that you can say that there's systems, how and when would the second law arise? And is there situations that are driven and open that would never create a second law?
I mean, I don't know the answer to this question in full generality, but it depends on how you construct the microscopic model. But I mean, if you do kinetic theory, the plain kinetic theory, the second law emerges. So if you start with that, this is the story of Boltzmann resummation and all this kind of stuff, then there the second law emerges. If you try to modify those systems to account for this kind of active structure, probably, I would say, you could see this showing up. If you do other kinds of microscopic things, then it's a good question of how do you compute the entropy to begin with. But there's a lot of literature on this. Also in StatMech, of how you start with single particle systems, then you go into Boltzmann kind of equations, and then there's prescriptions also in the active literature to try to compute the entropy for this kind of systems. There's controversy, or there's maybe not full agreement about everything, but there is a way of how to compute entropy. But I don't know if you just start with an arbitrary Hamiltonian or something, or even in these lattice models that I showed you, I don't know how to get the entropy out.
So in the simulations, you have no...
No, I just started to look at just diffusion and these simple models. So there, I don't have it. I mean, I didn't have a microscopic system that I coarse-grained and get an entropy out. But I'm just motivating the models with a microscopic system. And that's actually the answer to why the Netherlands should be in that plot, is because you can model social segregation by hopping and political polarization by particle exchange. So these are famous models in statistical physics. That's called Schelling model, the Voter model, So people take it serious and they try to constrain it with data. But I just want now to, forget about the microscopics. I just want to use the codes and improve them and extend them to the full system I showed you, which is already in the hydro regime. And I'm not being super concerned about how do I get the entropy from a microscopic model, though that's what also we're trying to look at in these modifications of stochastic heat exchange models. Because they're supposed to really describe energy and energy diffusion, and there has to be a way of being able to define this entropy somehow.
Can you do that when time translations are also spontaneous?
That I have no clue. But I heard there was a talk here by Akash last week, and he talks about spontaneous symmetry breaking of time translations in the context of this SYK change in the paper. But I haven't looked into this. I have no feeling about what that would make and do, and whether it's even consistent, I have no feeling about it.
Let's thank Jay again.